Hi everyone, it's Mr. Wilson. It's week 7, so we're going to do some week 7 problems. And these are about hypothesis tests. So they're kind of long, so I'm going to do this quick question 4, and then we're going to do one example each for a hypothesis test about means and then proportions. So let's start with number 4. The p-value for a hypothesis test turns out to be 0.06356 at a 9% significance level. What is the proper decision? So let me get my drawer going here. All right, so what is a p-value? So in a hypothesis test, the p-value basically says, okay, if we were to repeat this test again with a completely different sample that's also representative, random sample, the probability that we would get an extreme or more extreme result than the first time around is the p-value. So when p-values are low, we would expect this to be okay. This is an unusual result based on the assumption that the null hypothesis was true. So at the 9% significance level, we can rewrite 9% as a decimal, 0.09. So we're saying that's our cutoff for this test, for this experiment. We're saying, okay, if our p-value or our probability is less than 0.09, then we're going to reject the null hypothesis. So we're going to say, okay, that's where we're cutting it off. We're not going to expect to get a more extreme result or just as extreme on a similar experiment the next time around. That would just be too unusual. So we're going to reject the null hypothesis if the p-value is less than that significance level. So in this case, it is less. 0.06 is less than 0.09. So that is when we reject the null hypothesis. All right, let's actually do a test here. The state of Connecticut claims that the average time on death row is 15 years. A random survey of 75 death row inmates revealed that the average length of time on death row is 17.1 years with a standard deviation of 5.7 years. Conduct a hypothesis test to test the state of Connecticut's claim. So this is a mean. Mean or average time on death row is 15 years, so this is going to be a t-test for a mean. So when we're deciding whether we're doing a left-tailed, right-tailed, or two-tailed test, we're looking for those key words like more than or less than, or longer than or shorter than, that type of thing. And we don't have it on this one. It just says the test that the average time on death row is 15 years. So that's going to be our null hypothesis that it's 15. And since we don't have a specific more than or less than, then it could be either one for our alternate hypothesis. So in that case, it's always a two-tailed test. All right, we need to calculate that p-value. So I'm going to switch to my calculator. And this was for a mean, and we have the summary statistics. All right, so these are just sample values that come up, so we just have to type over that. Our claim is 15 years. Our sample mean showed 17.1 years with standard deviation of 5.7. I think our sample size was 75. Click calculate. All right. So there's our t statistic. There's our critical values. Our one-tailed, two-tailed, and we want our two-tailed probability with the uh, null hypothesis being that the mean is 15. So this is the one we want, 0.002, and then some more decimals. So I'll just type that in. So I want to switch back to my problem. All right, so this question is kind of strange because it doesn't give you a significance level. So if it doesn't give it to you, you're just going to assume the standard significance level, which is 0.05. That's a very common one. In this case, 0.002 is smaller than 0.05, so we are going to reject the null hypothesis or reject the claim that the average time on death row is 15 years. All right. Let me move to my proportion problem. Test the claim that the proportion of men who own cats is smaller than 20% at the 0.05 significance level. So that's a pretty small significance level for something that's not a life or death situation. Like you would want a small significance level for testing new drugs that treat some terrible illness. But for something like this, men that own cats, I would choose something that's larger, but this is what we're dealing with. All right, so we look for those keywords again, and this time we have one. Is smaller than, or is the same as is less than. So we're going to look for an alternate hypothesis that contains a less than symbol. So we are dealing with a proportion, so we don't want to use the ones that have mu. The Greek letter mu is for the mean. And I do see one, the second choice, where we want to test to see where the alternate hypothesis is that p is less than 0.2. So this is a left-tailed test. So whenever it's less than in the alternate hypothesis, it's left-tailed. If it was greater than, it would be right-tailed. So we'll select that part. And now we have our sample size, which is 100, and our sample proportion, which is 17% or 0.17. So this one asks for a test statistic and a critical value. So let me get the test statistic. This is the proportion one. So I'm going to click on the hypothesis test for a proportion. Ooh, I need to find a different one. All right, I will get that calculator replaced in the lecture notes. Sometimes calculators are taken down, or the sites make you want to subscribe or something like that. So if you've ever seen a calculator link in my lecture notes that isn't working, please let me know and I'll fix it. So this is the one I'm going to use. I will update the notes. This is our hypothesis test for a proportion calculator. The sample size was 100, and it wanted the number of scores with a trait that we're looking for, in this case, men that own cats. The proportion of men that own cats is 17%, so 17% out of 100 is just 17, so I'm just going to enter that in there. The null hypothesis is the probability is equal to 0.2. That's what we're originally claimed was true. This was a left-tailed test, so that's also called a negative one-tailed test. And our significance level which is kind of silly, was 0.005. Run the test. So this one didn't ask for a p-value. It's giving us the test statistic as one of the blanks to fill in. So negative 0.75 would be our test statistic. So let me enter that. Negative 0.075. All right, so this one asks for a critical value. So the calculator did not give me one. Let me just switch back to that real quick. So yeah, some of them do, some of them don't. It's easy to find otherwise, but let me just explain what we're doing here. So if we draw our little normal distribution here, let me actually draw it on the page. And we're doing a left-tailed test. We want to find the z-score that is the cutoff to where we reject the null hypothesis. So we're looking for, say, this z-score such that the area to the left is the significance level. In this case, 0.005 of the entire whole bell curve is going to be the area that we reject. So my drawing isn't great here. The 0.005 of the bell curve is just a tiny little tail off to the left. I just wanted to accentuate what we're exactly looking for here. We're looking for that z-score such that everything to the left has an area of 0.05. So that was the inverse norm calculator, and that was in the previous week's lecture notes, so I'm going to switch back to that. Yes, this is the one we wanted, the calculating data values from the given probability. So I'm going to click on that one. We want an area of 0.005. We want the standard normal curve, which is a mean of 0 and a standard deviation of 1. And we want below that. So negative 2.5758 is our critical value. As we can see in this diagram, it's just this little tiny bit that has an area of 0.05 on the left. Negative 2.5758. All right, so this is the z-score that we're looking for. So this z-score is negative 2.5758. And we're looking for, is the test statistic in that region to the left of negative 2.575? And it's not. Negative 0.075 is pretty close to the mean, be right about here. So it's not in the test statistic. So, or the test statistic is not in that area. So in this case, we're going to fail to reject the null hypothesis and say there's not enough evidence to say that the null hypothesis isn't true. We can never prove that the null hypothesis is true unless we have a 100% sample of our entire population, and that's always impossible. So we can never prove something is true with just a sample. We would just say there's not enough evidence to reject it. All right, that's enough for today. I will be posting some more videos next week. Again, if there's anything you want to see done, let me know and I can post a new video.